time for another DraftPhysics.com video presentation. Yeah, a little jittery, but it'll do. New computer, new used $100 computer, should be here today, so later. So tomorrow's video should be, hopefully, more back to regular. Anyway, superfluous information. So some comments. Totally not very useful as is typical, and it sort of is amazing, you know, just how little interest people have in physics and understanding reality and all that stuff. Just they have a great deal of interest in drama and insults and buffoonery, but yeah, not so much in anything real. Yeah, real conversation, nah, not so good. On the subject, nah, fuck that. Who wants to talk about subjects? Subjects aren't important. Anyway, so whatever this is, troll account 59,642. You tell us. So I don't know who us is. You know, is what? You know, how you would capitalize on a free energy machine. I mean, it's really not that complicated. You just say, like this video, I can just basically patent, okay? See, I mean, patent law isn't as complicated as you think, you know, in the sense that you don't really have to file a patent, okay? You really don't. All you have to do is prove that you thought of it first, and the judge is going to give you the patent. I mean, it's sort of, that's the way it works. I mean, the truth has to some way, you know, technically by the law, the truth matters. Now, judges can do whatever the hell they want, so, you know, who the hell knows? It just depends. If they don't like you, then yeah, they can screw you over, and there's nothing you can do about it, okay? Because there's nothing watching the judges. There's no judges watching judges to make sure they're not stinking lousy, constitutional rights violating pieces of dumb, ignorant shit. But anyway, that's we created a system that's just all political and all, you know, about this stupid, you know, Starbelly Sneetch shit. You know, the Starbelly Sneetches will make one law that applies just to the non-Starbelly Sneetches. Anyway, so the idea is all you want to do is be able to prove you thought of it first, and then you own any use of it. So I will patent Professor Lewin's experiment, because see, he doesn't have precedent to it because he didn't realize it. So he didn't think of it first. He didn't realize that, oh, I just invented free energy. So I'll patent the idea right now that if you put a spring in between massive objects and push energy in one direction, the spring will keep the energy in the same direction, but it'll compress for free and impose extra momentum on the heavier object, therefore creating free energy. Okay, there. That's my patent. Sign it with my DraftScience signature, because that's who I am on the internet. And you know, that's why I have a screen name, is for it to be used. There, it's my patent. I thought of it first. Yeah. Anyway, so it's not that complicated. Anyway, and I will show you a free energy machine. So whatever this means. So you're only in it for the money, right? You don't care about science or any of that kind of crap, and so somehow I have to give you exclusive rights to something, or I have to show you how you get to capitalize, you know. Or you're just going to keep your little secrets from the world of science, your little science secrets. Then he says free energy is real. Okay, it's a great assertion. I'm tending to agree at the moment, just because, well, what else can I say, right? A highly paid MIT professor has pretty much proved it. So I guess I have to say it's real, right? Has anybody got a counter argument why that would be unreasonable of me to not take Professor Lewin for his word that he did a good experiment, and that's what it, you know, it is what it is. He physically proved it. So, well, who am I to disagree? So you explain why I should look. You should post a comment explaining why I should say, oh, that experiment was a pile of shit. Well, explain how it was a pile of shit, and then I'll maybe agree that, oh, okay, now I get it. But until you do that, I'm stuck with it, aren't I? So anyway, just useless drivel. then V, whoever the fuck that is, whatever the fuck that is. Unless there's an error with measuring these times in Lewin's video, it does seem like you're getting extra momentum. Yes, which is not a good thing. Oh yeah, I will be getting to the Sumner video. That's the real agenda here for today. Could be the ping pong paddle type thing happening within the system. Yeah, that's sort of what I would argue, is that the spring's compression is somehow not work because it's in the same direction of the motion. And so somehow the energy is being conserved in the compression of the spring, which is, interesting. And so then you're able to do the pushing twice. You first push the spring, it compressed it, stored energy, and then you push the other object, and then the spring released its compression. And so somehow you got the compression for free. There's no way you can explain it. Now, whether it's really happening or not, it's another question. On the atomic level, yes, okay, the force stored within the spring is amplified. Well, see, now it's not amplifying the spring's force. It's just doing it for free. So the point is you got the compression of the spring somehow for free. So everything else would be just fine if you take out the spring's compression. The spring's compression is what creates the reflection 1/3 and the extra 1/3 momentum in the 1/3 velocity in the other direction. So the spring is giving you the little boost. Somehow in this circumstance, how exactly, I have no idea. It could also just be an error. Reasonable enough. Okay. Yeah. Thanks. I guess. Sorry, I don't want to. I just said yes. Okay, I sort of already posed this as being a question that needs an answer, and you just rephrased the question and said, "Yeah, it's a weird question, isn't it?" Yeah, it's a problem, isn't it? All right. Anyway, so how do you increase momentum without adding energy? Question mark. I just showed you how. I mean, that's exactly what the video is doing. It's showing you exactly how to do it. I don't know. So I said, apparently you just have to add a spring. Apparently. Now, isn't that the whole point of me pointing out that Professor Lewin says this is the formula for a elastic collision? Now, we already know that the carts were 100%, by most rational standards, elastic, and that they're made out of metal. So they're already very, very elastic anyway. And so he puts a spring on them, though. Why? If they're already elastic and they already fit for the formula, they're already supposed to produce the result without the spring. The formula says this is going to be the answer, and that's for elastic collisions. The carts are already elastic. So we have a new term we have to add. Super elastic or ultra elastic or something. That's when you add a rubber ball or some other spring device. So, this is where you're saying this is like basic physics, right? And they can't even get this stuff right. I mean, they're calling a steel ball the same thing as a rubber ball. They're obviously not the same thing, Anyway, and you people are just completely okay with that. Oh, it's okay if physics doesn't know the difference between a tennis ball and a steel ball. They're the same thing. Anyway. So, clearly this language is completely broken. But the key ingredient is obviously the spring. Okay? The spring is what made the difference in the experiment, because if you did it without the spring, I don't think it'll work. Okay, anyway. So then this idiot says DraftScience, question mark. Apparently you just have to add a spring. Apparently. What's the question mark about that? I'm answering your question. You said, so how do you increase momentum without adding energy? I said, you add a spring. That's the only thing we can blame in the experiment. It's the only thing that's kind of like, why is it there kind of question you can ask. So that's probably the cause, right? I'm out. You can't follow along at all? Anyway, and then the James Hines guy says, ask gravity. What the fuck? So I think I'll just block him, because that's just, the useless first comment and now this useless pile of shit. Fuck you. What the hell does gravity have to do with that experiment? Just nothing to do with the experiment. So anyway, part of me just says, well, why not just delete this moronic thread? But I might as well leave it there for everybody to marvel at and just say, what the fuck is going on here? All right, so don't give in to the assholes. It's a different, not physics subject, so fuck that. All right, so we will. That's it. That's all the comment there is. So you show a paradox. It's right there in front of your face. Doesn't make much sense. Can't do much with the theory, and you all just sit there. Yeah. Not interesting. Okay, what can I say? I think it's a little bit interesting, but anyway. All right. So I will pause and go to Sumner. I just watched there's a Royal Institution video they kept promoting, on my, on the related videos on rocket science. And it was one of those Christmas lectures, I guess, where all the kids, kid videos. So it's a kid video on rocket science. Now, I didn't say there wasn't anything I learned in that hour, but everything is just geared to being, too stupid. A gimmick, But anyway, the whole hour didn't mention kinetic energy anywhere. So just to point out that kinetic energy don't have much to do with rockets. Doesn't have much to do with reality. All right. So anyway, moving along. Alright, should be back. So this is Julius Sumner Miller, kind of an eccentric character, blah blah blah, explaining physics again to kids, but it's all we got. So we'll use it.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the very special third law in Newton's three laws of motion. And to view it at least once in our lifetime in the Latin, I have it here.
Okay, so let's understand. If they applied this third law and mixed it with kinetic energy, right? Now, if you attempt to do this third law video in the same context of doing a kinetic energy video, it would all fall apart because the third law can't have anything to do with energy, kinetic energy, because the numbers don't make any sense. It means there's 2,000 joules going this way of energy and only 4 going that way in the case of the gun. So clearly the third law can't mean anything if we really do, if Leibniz was right about what energy is. The third law can't mean anything because it doesn't have anything to do with energy. It has something to do with some kind of thing that doesn't matter, this momentum crap.
Lex 3. Actione contrariam semper et equalam esse reactionem. Now, if you didn't know any Latin at all, you'd see something in there about action and reaction. And indeed, that's what it sums up to be. Third law, to every action, there is always an equal and opposite or contrary reaction, or the mutual...
So let's understand. We'll do the or because it might be more important. So this isn't about action and reaction. It's certainly not about anything called a reaction. So the argument is, if you give it away, you don't need a reaction to have lost it. When you gave it away, you lost it. Okay, so if you make a rich man, somewhere in the world you made somebody else poorer. It's just a fact. Okay, the resources are the resources, and somebody has them before you get them. You can't have them and pretend they're brand new resources. They're always somebody else's resource, somebody else's labor, somebody else's something. So if you're making rich people, you're making poor people somewhere else. That kind of logic. And obviously that's the kind of logic people don't really have. So it is kind of funny that they can't think of the physics right or any other circumstance where you would understand that you don't need an opposite reaction. You just need the action. The action is all there is, and the action has built into it the reaction. I give it away, I don't have it anymore. That's simple.
Actions of any two bodies are always equal and oppositely directed.
Okay, so it just isn't true. And what it's really saying is what Newton was tangentially falling on as a truth, the real truth, is that actions in their elemental form are always an explosive kind of event. That there is no such thing as the universe just doing this way, in the elemental sense. electrons expand in all directions. Balloons blow up in all directions. They expand in all directions. Since everything is just an expansion and a contraction, you can understand in the universe, anything we call energy. So every real elemental source of functional energy is always going to be in a form where half of it goes this way and half goes that way. And then if you want to be really technical, you have to look at it dimensionally. And so yeah, a third of the energy goes in that dimension, and a third of the energy goes in this dimension, and a third of the energy goes in that dimension. So if you want to say the total energy, just like the sun is producing energy in all directions. We can look at it in just two dimensions and say, relevant to us, okay, yeah, there's energy coming right towards us, energy going away from us. Okay, so it'll look like, the third law, but it's not really the third law. It's just the idea that the universe doesn't do, I'm just doing that way. It doesn't do anything but expansion and contraction.
Now, a strange introduction to this law would be as follows. Consider me standing still and quiet on the earth, and I jump up in this manner. I ask, did you feel the earth recoil?
No, but I laughed the first time I saw it. I mean, I really did. So in a sense, I recoiled with a little bit of a chuckle because, yes, it really was quite eccentric.
And the answer is, it must be, it did indeed recoil, even though you may not have felt it. Why?
And for some reason you had more energy because you're smaller and faster. So you had more joules of energy somehow, but you didn't really cause the equal and opposite joules into the earth.
Here is the earth, enormous mass. Here I am, a teeny weensy creature of little mass. I push down on the floor with a force F, which acts on me and on the earth. And, as before in the second law, my little mass, you detect, has an enormous acceleration. Up I go. But the Earth, having an enormous mass, has a teeny-weensy acceleration, which you cannot detect.
Right, and there is a point, though, where, this is not a logical argument. You could understand that there is a point where the object won't move. So let's say, if we had these things in space, you could sort of see it more perfectly, adding a tiny bit of an influence and seeing if you're getting actual movement out of an object. Because there's a point where all it's going to cause is jitter inside of the object. The energy can't get all of the atoms to move in the direction you put a force in. You put a force in, all the atoms won't go, so all the energy can do is reflect inside the object. Go from one side back to the other side, push electrons out. The electrons can't drag the atoms with them, so the electrons have to go back in. When they go back in, they push the electrons on the other side out, back and forth, back and forth. So there is some critical point where a mass goes from being capable of actually moving to it isn't going to move. Okay, it's just going to sit there and vibrate. So they're, and they don't even get that. I mean, you can sort of understand that has to be true, right? It doesn't take like an infinite amount of time, and it moves it infinitely slowly. There's no such thing as infinitely slowly moving, right? So you can sort of get that now there's a point where it just doesn't go anywhere because it can't make all the atoms go. If it can't make all the atoms go, then none of the atoms go.
So, consider Newton's third law in a toy. Here is a little vehicle with some wheels to which is fixed a rubber balloon, and I blow some air in the balloon.
Insanely lame toy, by the way. I think I had one, piece of garbage, doesn't go very far, doesn't do much. Not very interesting. Might entertain a silly cat.
Now I'm going to let the air come out of a certain hole, orifice here. The air comes out this way, and what must the vehicle do? The vehicle must go the other way. Watch it. There it goes. And so, I am reminded of a certain exercise that goes like this. Here is a rocket vehicle. We have some stuff in here in a state of combustion. The products of the combustion come out here. Millions of little particles of stuff. Now, many people have the distorted notion that this...
Okay, talking about distorted notion. So apparently some people have the distorted notion that thousands or millions of joules of energy can go out that end, because it's going faster. So you have little bits of mass going faster, then you have a whole big pile of mass going slower, and they calculate that the little bits have more energy than the big bits going slower somehow. So obviously it violates the third law. This doesn't make any sense. You can't use rockets to explain kinetic energy and the third law if you keep kinetic energy as a real concept. So that's why he's narrowed the conversation to momentum, because yes, momentum makes sense. Kinetic energy doesn't make any sense. You can't make rockets make sense with kinetic energy because there's no more Newton's third law.
Stuff coming out here must push against the atmosphere in order for this to go. And I say that is utterly erroneous. This system, this vehicle works better where there is nothing, because we want the little mass of stuff coming out there to come out with the greatest possible velocity, and hence
Right, you want no back pressure. You want nothing to be in the way of those particles being able to leave. That is, so if you clog them, if you stop them, if they have to bounce off something, they're going to create a back pressure that's going to push particles back in. Some particles, some small number, but it's still a number, and that's still lost energy. So any back pressure is completely negates your intended purpose, which is to release stuff going in one direction. And therefore, you know, as I've sort of illustrated or tried to point out, I believe I can, let's see if what do I have to hit? I forget. Well, anyway, I could draw it, but it's, I'm probably asking for trouble, but I'll try. It's all for the cause, right? Let's see, does this work? No. Does this work? Yeah. Okay, so if it was bouncing around inside here, and that's a really bad angle, so it was bouncing, it went from here, let's say, okay, so it went from here, and it bounced off here, and then it went right to this front, and now it's going to bounce.
at the greatest rate of change of momentum.
Okay, now it's going to bounce this way, out. All right, so you can sort of see that its last move was in this direction. I gotta do it.
Product of M and V being momentum.
Sorry, technical. You gotta do this in the right order. So the last move was this way, right? So
now I'm going to go back to the car.
So anyway, so that's going to be the one that's preserved, right? The one going that way was the last action. So the last act, while it was in the ship, is this way. The last thing the ship knew was go this way. So that's what happens when you release it that way, is that you leave a last act inside the rocket. So if you open just a hole in this direction, and only stuff that is going this way can get through the hole, right? I mean, stuff going this way can. Stuff going this way can't get out the hole. The only stuff that can get out the hole is stuff going this way. That means the last act it had was that way. That's why the rocket moves. Now, to me, that's a great explanation. Should be in the Royal Institution when they're going to explain how a rocket works. That should be part of the illustration. Should be this example that you're just letting the energy out in one direction that would have equaled the other side. So it got hit this way, and you're taking away the equal and opposite. You're taking away the force that would have balanced this. Now you take away the balancing force because it just shoots out and doesn't balance, doesn't hit the ship, doesn't balance the ship. So now the ship has an imbalance in this direction. I mean, it's a much clearer demonstration of a model, a much more sensible, in my opinion, explanation. All right, continuing.
Because the case of the two cars I said earlier, very important. Massive car, less massive car. I stretch the spring between them. One and the same force acts on both. And we witness an astonishing thing. Here is the massive car. Here is the little car, less inertia. There is the spring. Now, what did we see? The same force acted on both.
Well, we barely saw anything, really. But, okay, the idea is the little car is going to go twice as fast as the big, massive car. You know, and there's all kinds of argument that the truth is something else, but no one can show the truth to be something else in any kind of, credible way. Okay, so they can make flat earth claims about how it makes a difference whether one of the cars is nailed to the floor, but the counter argument is no experiment shows that it makes any difference.
But you notice
no credible experiment done by anything like a decent human being who can behave basic civil rights respecting civil behavior. Yeah, that kind of person can't do it.
that the smaller one had the bigger acceleration, and the bigger one had the lesser acceleration, and therefore...
So, you know, he's using the word acceleration, which is sort of just, that's not Newton's word. And, you know, the key concept, though, is the fact that, yes, you will acquire a change in your velocity. And the acquisition of the velocity, you have a velocity through the process of acquiring velocity. Your velocity increases. It's an amount of something, and you get more of it as the force is applied in one direction.
In the same time of travel, and they would both travel at the same time, from time zero to the time of collision, clearly the smaller one has the higher velocity. So, writing the momentum of both cars, we would...
So, we already know this part, and it just seems a little strange that he does this, just because why go through the step of acceleration when all you want to get down to is the bottom line? What's the momentum?
Equate it as follows. The large car has a little velocity, the little car an enormous velocity, and these momenta are equal. Very important that you see that point, that the same force acts on both. The acceleration
All
are
right, so let's just understand, there's a whole bunch of people out there who say that is completely wrong, and yet they won't comment on this video. There won't be any comments in this video saying, oh, Professor, you got that totally wrong, momentum isn't conserved, blah, blah. No, there won't be anything like that. So, for whatever reason, they'll only attack, you know, peripheral people, you know, that make the claim. When the important and respected people make the claim, who cares? They go out and find some hillbilly in the middle of Arkansas somewhere, and because he says, I'm against, you know, something, they go beat him up. But they won't beat the politician up who he's saying exactly the same thing. Strange. Or the celebrity. You know, they'll just ignore him. Well, it's okay. He's still my hero. Yeah. It's just kind of bizarre. Just an example of typical human bug-like behavior, you know, where they can't even figure out, well, that seems like a hypocrisy and a duplicity. Why would I attack the irrelevant characters? Why would I go after the chef, you know, for the army or something? Why the guy who, you know, dusts the shoes or something? You know, they won't take on the guy who's got the guns and pointed at them, but no, they'll go pick on their wives or something.
Is the masses and the momenta are equal. In another program, I will talk about their energies, and we will discover a very strange thing.
Right. So yeah, the strange thing is that physics is really screwy. Yeah, it doesn't make any sense. You have two definitions of energy. It doesn't make any sense. Too stupid. Why don't you fix that? It's really broken. Blah, 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 blah. So, again, I'm just doing this to point out. I played yesterday the video after this just to demonstrate how bizarre the arguments are, because if he did talk about kinetic energy here, he'd have a real problem explaining the distinction between momentum and kinetic energy. Because they can't be the same thing, they get different answers, and they can't really be compatible because they really are describing the same thing. What will this thing do in the universe? How much energy, how much movement can you give other things? And they're giving you different answers to that simple question.
More on this conservation of momentum, which is essentially Newton's third law. Here I have a CO2 cartridge. Gas in here under enormous pressure. Here is a carriage in which I put it. I'll look around that end. And you will notice that there is a barrier on this end of the cartridge, of the carriage. Now what am I going to do?
So let's understand that, again, this is a demonstration. If he uses kinetic energy, this demonstration totally fails to describe Newton's third law, because it's basically saying there's a lot more action going one way, a lot more energy, than it's going the other way. The recoil is a tiny percentage of the energy expelled by the CO2 cartridge, because those little particles going fast, those individual small masses going fast, somehow have more energy than the collected mass going slow. That's their argument.
I'm going to make a hole in this end of the cartridge. The gases come out this way. Oh, I erased that before. The gases come out this way, and they have a certain momentum, their mass and their velocity. The vehicle
So let's understand the pressure leaves in one way, right? So the gas is the pressure, The pressure is, we know it's just molecular pressure. That means there's just stuff bouncing inside of the container. This container contains a substance that can't interact with the metal of the container, can't get emulsified into it. So it has to just bounce off of it. It doesn't have a choice. The energy just keeps bouncing off the interior surface, and the pressure is that interior molecular movement trying to get out. They're closer to each other than they want to be, like little magnets. You got a bunch of magnets too close to each other. They want to release their pressure, and you let it go out one direction, and every single piece that goes out the tail of that CO2 cartridge, every single molecule that ends up going out will be a molecule directly having its last act hitting something in the opposite direction, essentially. So obviously the molecules hit each other, so a molecule can be reflecting and then going this way, and it hits somebody going this way, and it makes them go that way, But the point will be, is the last act the ship knows of was this way. That's the last piece of pressure it knew before it lost a piece of stuff going out the other way that never hits it. So it never creates the opposite reaction. So in a way, the third law should be rewritten to say every action has an absence of reaction. You've liberated a pressure, you've liberated a force, and by liberating a force, its previous action still exists in the universe unbalanced. You have an unbalanced action.
Oh, the other way. Watch it now. Watch. There it goes. There it goes. Miller's earthbound rocket. Now, a very important thing. It fled away. Fled away. Momentum, I'm sure. I would have asked a question had I had it in hand. Question. I would feel it to be very cold. Very cold. And I want to know, why is it cold? A second question. There could indeed be...
Yes, that is kind of it's an interesting concept. The fact that once you've let all these little vibrating things out, there's nothing vibrating anymore. There's nothing hitting the surfaces anymore. So there's a lot less action in everything. But anyway, it's really not related to this momentum thing. So I guess posing those kind of questions, it's kind of irritating, just frankly, because it's a change of the subject.
Frost on it. And the question is, where cometh the frost? In the first question...
the atmosphere, that's where, yes. The moisture's, little water molecules in the air, and you can make them condensate if you make something cold.
We have a very powerful piece of physics. The gases coming out must do work. This costs energy.
Okay, so there's no work involved. They're undoing work. They're being expelled from a working environment to a non-working environment. They're being liberated, and they're taking their heat with them.
And I leave it there for further discussion in another program. Now, let's go to something still more dramatic. Again, conservation of linear momentum. Here is an array of steel spheres.
So this is a really crappy Newton's cradle, so it's kind of disappointing, the results, but I can use this to make my argument.
Steel is highly elastic. By that I mean...
Okay, so he's pointing out steel is highly elastic, but if you put springs in it, then it's even highly elasticer. Yeah.
When they are deformed, they recover. They lie in the lowest potential configuration. I take one up the plane, let it go, having given it some...
So it is a little bit silly to say steel recovers, right? When they deform, it recovers. Because we know the steel's, it's not really deforming, is it? Come on, get serious. You're not really deforming the steel, okay? You're sending a vibration into the steel, and you can collect the vibration on the other side and all that kind of stuff, or you can let it bounce back. But there's no real deformation of steel.
Potential energy, and it collides with a system at rest, and watch what happens on the remote end. One. Oh, that's terrific. Watch it. Look it.
So you just really, technically, you have one mass hitting 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you really have one mass hitting 9, a mass of 9. Right? If we tied all of these together, all right, if we just stuck them together, crazy glued them all together, then this becomes a Professor Lewin experiment, right? And so then I send the one bit of momentum in, and if all 9 of them were tied together and they weren't on a track, so they couldn't, you didn't need them to roll, and they were just swinging in the air like a Newton's cradle, The idea would be is that you put one momentum in, you have a velocity going in, and this 9 mass will collect a lot more than half of that momentum. So if it was just 2, so if I did hit 1 into just 2 that were glued together, the theory is that the energy goes in, it hits, it reflects with 1/3 the velocity, and the 2 balls would end up leaving with 3/4 of the original first ball's momentum. So I've created 1/3 extra momentum in this direction, and I have 1/3 free going that way. I'm just saying that obviously this theory should have been noticed by now, right? It just seems like somebody should have noticed it. Yeah.
Nearly instantaneously. Indeed, I'm led to ask, how fast does the impulse get down there? Answer, with the same velocity as the velocity of sound in steel, which is about 15,000 feet per second.
Right, so it's really, you're just talking about the vibration travels through it. So the energy is the vibration, the movement of electrons, technically electricity even you could call it. And it just moves, and if it has another surface to move into, then the electrons push those electrons, and then those electrons push the electrons of the next ball, and it's able to keep the force going without it reflecting back. And it reflects back, why? It's because in the last ball, if it doesn't move, the electrons have nowhere to go. They go out, they can't pull away from the atom, so they have to go back in. And that's your reflection.
So if this were a foot long, well, that's more likely a foot long, that's 9, 12 inches. Watch it. 1/15,000th of a second. You notice, too, that the whole system experiences some motion. That's because they all wish to seek a lower potential plane.
That's because he's got it based on a little curved arc, and it's not the best way to view it, frankly. I don't know why he's doing it in this form where he's only moving it a tiny bit, so I think it sort of defeats the interestingness of the experiment, but whatever.
Now, 1 at collision MV. 1 goes away MV. Watch 2. 2 MV plus MV. 2 MV. Now let us disregard the intermediate.
Right, so let's just disregard the fact that it really hit something that was 3 times more massive. 2, 4, 6, 3 times more massive. So it shouldn't have gotten the same energy, the same momentum in the other direction, because it's hitting a much bigger, massive object. And all we've really done is take this, all we're saying is if we attach those things to each other, that somehow we change how much energy will be realized. And that's just pretty strange to believe that's the truth. And then if we put springs between these objects, now we're talking about, well, what should happen if I put springs in series? That is, I put a spring on top of a spring on top of a spring. Well, then I'll just compress all 3 springs a little bit. So that won't work. You have to have space between them for the experiment. Like, say, if I was going to multiply it, and this was, I put 2 glued together here, and then 3 glued together next, and then 4 glued together after that. And I just separate them by a little bit of distance, and I put springs on either side of them. When I get to the 4 of them glued together, I should have more than doubled my momentum by Professor Lewin's experiment, by Professor Lewin's formula.
Or the other motions that we witness, because a discussion of this would divert me from my purpose here. All I wish to say is that whatever the momentum before the collision, so that is the momentum after.
And again, except when it's not, right? So what are you going to do? What do you say to this? Emphatic statement, but not really true. Demonstrate in Professor Lewin's experiment. I mean, the two are opposite statements, opposite arguments, opposite demonstrations. It's right there in front of you. Yes, this is very convincing. But so is the other experiment.
1, 2, 2, 3. Oh, notice they are seeking a lower potential plane. The energy of a system runs downhill. 3. Oh, that's pretty. Notice they are seeking a lower potential plane. 4. Watch it now. Notice they are seeking a lower potential plane, just as my energy is running downhill now as I do the show. 4. 5 up. 5. And so we say, without question, the momentum before the collision is equal to the momentum after.
Except when it's not.
Consider another classical demonstration of mine, which is easy to do and quite dramatic. Here is a steel pipe. This demonstration
This is so funny. Anyway, it's just very funny. This demonstration, that won't be a demonstration.
Call virtual. virtual. There are some demonstrations that I do for real, and I call them real demonstrations. This one we will imagine. And imagination is a very necessary ingredient of this business. We will imagine a steel pipe closed up tightly
Yeah,
on...
I imagine you actually doing these experiments more completely so we could actually get the reason why it happens. That would be interesting. Let's find out why by doing a few more experiments and manipulating things. Little stiffer springs, softer springs, different kinds of things. See what happens. See if you can tease the truth out. But no, can't do that.
One end with a cap, mounted on wheels, and in this chamber I put some dry ice, solid CO2. Then with a wooden plug, I plug it up very firmly, and I let it stand here on the table in the hot air of the classroom or the TV studio, and what happens? The CO2 sublimes, goes into gas or vapor, the pressure builds up more and more, the pressure gets enormous inside, something has to go, what goes? The cap, with an enormous velocity, enough indeed to kill a man. So if you should do this, I warn you, have some caution. And what happens to the vehicle? It goes the other way. Big mass, little velocity, little mass, large velocity.
Okay, but that doesn't work for kinetic energy because little mass, high velocity, high kinetic energy, big mass, low velocity, low kinetic energy. Somehow the quark can do a lot more work in the universe, so you haven't got an equal amount of work distribution, capacity to work. So what relevance can it be to say they're equal forces when how they could be equal forces? How can it be an equal action-reaction when the action can do more work in this direction than it can do in that direction? If the action has more working potential, how could they call the actions equal? I mean, does it make any sense? I mean, don't you understand that once they destroyed Newton's conception of momentum as being the truth by replacing it with kinetic energy, they also have to modify the third law and say this has nothing to do with the truth either. Because what's not conserved is the energy. It's completely not conserved, so just admit this conservation law doesn't mean anything. The third law doesn't mean anything if the real energy isn't what you're conserving. Some other momentum, whatever the hell that is, doesn't mean anything. If it can't affect the universe, if it doesn't affect it, what meaning could momentum have? It can't have any meaning as a word.
Conservation of linear momentum. Powerful business, powerful.
Meaningless business, meaningless. Okay, we live in the Leibnizian world where, man, it's meaningless.
Consider, toys have a large role in my business because the physics of toys is an enchanting thing to engage in. Toys, I would have you understand, ladies and gentlemen and boys and girls,
This is actually a good example because this is another example of what you can do with a spring, right? You can rotate a spring. And, it's not really compressing the spring in the same way, but it's creating lots of stored energy in the spring in terms of its size, stretch. And it's clearly an example, too, of something that can achieve a very high velocity. So a spring that you twist, torque, can produce even more velocity than one that's expanding, and therefore create a very high speed, convert the energy. So you put in a very low speed, low kinetic energy because you're not doing much work because it's all low speed, right? And you get something very high speed out, and so that's another piece of free energy, right? By kinetic energy standards, you put in very little kinetic energy because the motions are very slow, and you got out very high speed actions that are going to have a high kinetic energy. So again, another violation of the third law, another demonstration of the violation of the third law.
Toys are intended for child's play, but the physics of them...
the action and the reaction don't match. I put in a slow action over more time, and I got back a high velocity, reaction with much more energy.
It's hardly that. Here is a little propeller with some inclined blades, and I have mounted it in a chamber wherein resides a spring. So I am storing some wound up elastic energy in the spring, and I release it. I did that one prematurely. What happens? How is Newton's third law? How does it play a role here? Answer. The pitch blade engages the air, drives the air down with a momentum mv. The vehicle must go up. Watch it. There it is.
So that's not really the interesting part, right? I mean, why the propeller goes up isn't so interesting as it is how does it acquire that high velocity? A high enough velocity to do that, to fly. So, that's the part that's interesting. You put in very low velocity motion and you got very high velocity motion out.
Oh, that's a pretty thing. And then it's spinning as a top, about which I will speak in another program. So the question is to be asked is, how does a bird fly? Here is a bird fly.
Oh dear, now we get very eccentric once again. Kind of just too eccentric, right? This is a little too eccentric.
Here is a bird. I'm probably viewed as a vulture. Bird. I can only fly.
Dodo. Yeah. You just need to get off the ground just like a dodo.
If I push the air down, and that's why I go up. Now when a bird soars, as they do ever so gracefully, that is quite another thing, again, to be considered subsequently. Or a balloon. Here's a balloon. Incidentally, I'm going to do a program on bubbles and the like, and I will raise the question of why is it hardest to blow up a balloon at the very beginning and easier to blow it up the bigger you get it. But anyway, I put some air in there. Now,
well, because you have to stretch it. As you stretch it, its bonds get weaker and weaker because you're pulling things apart. So it's like getting the magnet further from the center. Once you go away from the center, it gets easier and easier.
If I let the air out here, momentum mv, momentum the other way. There it is, like that. And one last exploration. So
again, I did that already in the beginning of the show. It's the same thing as what you could argue is the rocket, and really the answer is you let the stuff all out in one direction, and the direction it was going previous to that was the opposite direction. So that's why the balloon goes the other way.
Last exploration.
I mean, you gave it away. You gave away substance in a direction, and the only thing that was significant about the substance is it was moving. That's the reason why it's leaving, is because it's moving. And its last movement was going this way. That was relevant to the object containing it. So the only thing the object containing it knows is it keeps getting hit this way. And it doesn't seem to be getting any hits this way. They all miss. So the fact is it just knows this is what it has left over. So it's not about an equal and opposite reaction. It's about this action, and then you took away that action. There is no opposite action to balance. I'm just saying the truth is just so much more interesting than this vague statement saying equal and opposite force thing. That isn't really the truth. It doesn't really explain the mechanics.
Hero's engine. Here is a little vehicle you can make out of a tin can. You put some tubes through it. And
solder some tubes. Why would you bother? Okay, so this is, Professor Lewin showed this. I mean, this is somehow really important to physicists, but I mean, it's just so, you've already showed us that letting the pressure out in a direction is the whole game. And so as this thing rotates, it's going to keep adding momentum, along the vector of the rotation. And so, yes, it's just, you're letting the energy out in all kinds of directions, but it's always, now that you have it on a spindle, it doesn't matter that it's in different directions because it's all tied to rotational momentum.
The tubes at right angles to their lengths. Put some water in here. Boil the water. The steam, more exactly vapor, which becomes steam on condensation. The vapor comes out the orifices, and this turns around ever so fast. This is a substantial demonstration of Newton's third law. And here is a bigger scale one.
Okay, so again, it's really not. It's a demonstration of what happens when you imbalance a system, not balance it. Equal and opposite reaction, you really have a very uneven action. One action happens inside the container, the other action releases it from the container. Those two opposite, that one action, what's the last thing you did, versus what are you doing now, those two things are so different. The last thing you did is hit something. The thing you're doing now is not hitting anything. That's where those two actions are very different, even though it's just one action, though, that caused it.
On which we could run a very quantitative experiment. so much water, so much heat energy put in, so much energy gotten in the angular velocity of the vehicle.
Right, and then why don't you do that? So he just says we could do a very quantitative experiment, blah, 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 and then we could what? We could prove kinetic energy then, right? See, that's the only way to really do it, is to actually measure your outputs. Actually measure how much, how many light bulbs, a 10-ton train going 5 miles an hour could light versus a 5-ton train going 10 miles an hour. He's pretty much overtly saying they should light the same light bulbs, but kinetic energy says, no, the faster one should light twice as many.
And so, what must we now say? We have explored, in the passing shows, the first law in 2 parts, the second law, which is wrapped up in F equals ma, and the third law, referred to as action.
Right, now I'll just argue. The real truth is there is no F equals ma. There's F equals change in momentum over any time unit you wish to use. Per second, per hour, per year, per century, per forever. And if you use per forever, then your answer really is the force equals the momentum.
And reaction, which I will close in this way. Here is a very freewheeling vehicle. And you know that if I stand on it at rest and go forward, the cart must go backward. Which it does.
Right, so, but this argument has to do more with friction. Well, anyway. The principle is the same. I'm just saying that obviously, how did you make your foot go that way in the first place? You had to create an imbalance in your system.
And I say that when I walk this way, the earth goes the other way. I thank you for your attention.
Well, clearly it doesn't, but whatever. So enough said. Blah, 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 blah. So it just does an illustration. So, I mean, this is all we got are these things. So I'm just saying there's a bunch of people who are harassing me that I don't know any physics and I don't know what I'm talking about and all that kind of crap. And they all have a theory that this guy is directly contradicting, saying isn't true. And yet, why aren't they commenting on his video, pointing out how the physics is very badly being taught? Why are all these people saying thank you, and whoa, what a great guy, and oh, the physics is wonderful, and oh, this is so cool, oh, it's so great, it's all so good, when he's teaching really rotten physics by their standards? So I'm just, can we ask the question, why don't they care that all this misinformation is on the internet? Yeah, okay. But they do care about, my personal life. Yeah. They don't care about that, but anything that has to do with what is my personal information or data, they seem obsessed with. Very strange. Very, very strange. To call that anywhere like rational behavior anyway. So obviously it's bug behavior. So it does prove my bug theory. Humans really haven't evolved past being just bugs. And fairly ugly ones, frankly. We're not even pretty colors. Anyway, so till the next time and such and so forth and whatnot. So this has been a Draft Physics video presentation. Till the next time and such.